Hey, Space Cadets, you've all seen this. As Scott Manley humorously said, it was the first time that a rocket had taken off from Norway and landed back on Norway on the same day. Hey everybody, hi Scott, you're absolutely right, but you're missing the full story. Why and where did this rocket fail to take off from? Well, it took off from this strange place. It's called Andøya, or AXA SL9. If you're an SR-71 pilot, you'll know it well. This is NATO and Norway's most secret spy base and secret physics laboratory. Ooh. Ever since I got pointed in a very interesting direction while investigating the Rendlesham Forest incident, a number of people have said to me, you need to be looking at Norway and Finland. Why? Because Norway and Finland have weaponized the ionosphere. So what's all that about? Well, a very smart person in Germany a long time ago discovered that radio signals bounce off the upper atmosphere, or the ionosphere, like a mirror. And they sent a message all the way to Denmark, I think it was. That ionospheric bounce propagation of radio is the basis of all radio long-distance telecommunications. Ooh. So it needed to be weaponized, absolutely, to stop those pesky Soviets sending radio communication to their ships and submarines. And that's what people tried. In Norway, in this place where the rocket didn't quite take off properly. So you've all heard of HAARP in Alaska, but you probably didn't know about IceCat in Norway. IceCat was used as a European ionospheric heater. It was based at a very remote place at the far northwest of Norway. Andøya, the very place that's now doing space launches and continues to do ionospheric heating research. And HAARP and Andøya weren't alone. There's lots of ionospheric heaters around the planet, probably in Antarctica. And one of the least known stories is why the Falklands and Ascension Islands were Britain's part of ionospheric blocking in the Atlantic. The idea was to put up a fence right down the middle of the Atlantic. And the first part of it was from the Falklands to Ascension Island. And the second part was from Ascension Island probably to Greenland. I don't think that was completed, but certainly the Falklands to Ascension Island was actually done. On the Falklands or on British Navy ships were nuclear-tipped rockets. They exploded over the South Atlantic and sent up a pulse all the way to the Ascension Island to build this wall, to stop telecommunication, and even to stop ICBMs being able to be talked to during their re-entry. The big idea was Falklands to Ascension Island, I think probably to Greenland, a fence to protect the east of the United States. And then, in the Pacific, the same nuclear ionospheric bombs were tested off the coast of Hawaii, and the so-called rainbow bombs were seen in the 1960s, again to put up this ionospheric shield, this time over the Pacific. None of it worked very well, and in fact it was banned. It did a lot of harm to our planet and the ionosphere, but they kept the ionospheric research stations open. HAARP, Antarctica, and one in Puerto Rico called Arecibo, and then in Europe we have IceCat. So meddling me has been looking into what IceGet did in the past and what it does today. Here's a wee film I made a year ago about Andøya and what actually goes on there. And also a film with the head of Finnish Ionospheric research. I like digging for you because the truth needs to be out there.
A resident of Andøya goes outside to film the Northern Lights when the peaceful scene literally explodes. 4 balls of bright light erupt and seem to drop 4 glowing objects to Earth. Then, watch, just as it starts to fade, 4 more blow up. Is it a UFO? But these just hang there as their glowing payload falls to Earth. That's anomalous even by UFO video standards.
I've often said that the real truth that is out there will be revealed on your mobile device, on YouTube or whatever, filmed by somebody with a mobile phone. Today, you and I just saw it. Here's the same place. Andøya, Norway. What's special about this place? A lot. Andøya, Norway isn't just some town in Norway that somebody filmed a UFO. No, it's the site of the Norwegian and NATO and the US Air Force's most secret Norwegian base, including SR-71s. This is a log of SR-71 off-base landings. Where did they land? Andøya, Norway. So why did this ring a bell with me? What's really going on in this picture? What you're seeing here is not a UFO. It's a man-made ionospheric effect from one of the world's biggest ionospheric heaters in Norway. And this rural town in Norway isn't what it appears to be. It's actually the Norwegian base for the US Air Force and NASA from Wallop Island. And because it's Norway and because it's NASA, they published exactly what they did back in 1979 and 1980, just a few weeks before the Rendlesham Forest incident. And obviously that research continues to this day. And that's what this guy filmed. Look again carefully at these images of what he filmed, his UAP. First of all, a geometric pattern, a man-made pattern of lights in the sky, plasma effects. But what's really interesting is what happened next. Look at this effect. Look at what's dripping, apparently, out of the plasma. What you are seeing here has been described many times by people who have encountered the highly strange. The lava-like things descending out of the glowing light. That was seen and described by the witnesses at Rendlesham Forest and the crash Landrum case. This, I believe, and present to you today, is the evidence that we've been looking for, a military connection to ionospheric messing around. High-energy physics injected into our ionosphere to weaponize the shield around our Earth, to control communication, to deorbit satellites, and to produce strange effects. I think what you are seeing in this case, innocently filmed by a Norwegian bystander, is the ongoing high-energy physics of ionospheric weaponization. Well done for capturing it.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power. And liftoff of Starlink. Go Starlink, go Falcon.
Another successful launch of a Falcon rocket with a bunch more satellites for Elon Musk's Starlink constellation. What no one knew that day was that 33 of the 49 satellites would fall back to Earth and burn up in our atmosphere. Starlink is a constellation of LEO satellites. LEO, low Earth orbit. Most TV and communication satellites fly 33,000 kilometers above the Earth. But Starlink wanted small dish, two-way, low-latency internet communication. Their solution is to fly over 10,000 satellites just 500 kilometers above your house, well within the region we call the ionosphere. Just the same as before any flight, Starlink technicians checked the weather. Space weather. NOAA, or the National Oceanic and Atmospheric Administration, publish a space weather forecast, letting satellite, communication, airlines and utility companies know when the sun is more active than usual. But that day, Starlink misunderstood the full implications of the space weather forecast. A recent solar storm was heading towards Earth. Satellites in geostationary orbit might be mildly affected. But what NOAA's space weather forecast was not designed to predict was how the Earth's upper atmosphere was going to absorb the full impact of the sun's weather. 33 Starlink satellites were destroyed that day, when Earth's upper atmosphere expanded, caused more drag, and made the satellites fall back to Earth. The ionosphere is a fascinating part of our atmosphere. It's where Earth meets space, where air is energetically charged, partially turning into plasma, making it magnetic. It reflects radio waves, and it also protects us on the ground from the sun's high-energy particles. But the ionosphere is a dynamic system, always in motion, expanding and contracting, often reaching out as far as 600 kilometers into space. Understanding the ionosphere is an important science. Predicting its movement, measuring its magnetic effects on radio wave propagation, looking for military applications to potentially weaponize our atmosphere. And today, science needs to predict how this complex system interacts with low Earth orbit satellites. Finland has long been at the forefront of ionospheric research, building instruments to measure the sky in the 19th century. Maybe this inspiration was because Finland is under a northern sky full of auroral activity. And today this research continues in Finland at the University of Helsinki. They have a world-leading department studying space physics. I reached out to Professor Minna Palmroth to answer questions about our ionosphere. She kindly offered to talk to me, and I think you will find her knowledge and new research fascinating. So welcome. I'm so honored to have you here today. And the ionosphere is really so important and so misunderstood. My YouTube audience and people who are interested in science absolutely have heard of the ionosphere, and they get it all muddled up and they don't know what it is. They don't know where it is. So wonderful to have you here. And let's start with this most basic question is, where is the ionosphere? How far does it go out? And why is it called an ionosphere?
Yes. So ionosphere is shortly just the upper part of our atmosphere, the part of our atmosphere which is electrically charged in a way. So our atmosphere here on Earth, we have air which is not electrically charged. It's a gas which goes from one country to another country, and then you have winds and so on, temperatures and so on. But ionosphere is the upper part of the atmosphere where some of the particles in the atmosphere are charged. So there are electrons and ions basically, which makes this medium electrically charged, and therefore it has to be called with some other name than atmosphere. And therefore, because there are lots of ions, it's called ionosphere.
Oh, perfect. So effectively, a part of it
is a plasma. And the plasma is has negative and positive charges which can be affected by magnetism. And it gets this charge. Our atmosphere gets this charge, and it has become and partially ionized because it's right at the very top of our planet.
Yes.
And it's been, am I correct in saying it becomes ionized from the energy from our sun?
Yes, there are actually two ways in which the ionosphere is ionized. So plasma is the fourth state of matter. We have solid, liquid, gas, and plasma. And if you get heat, put heat to the solid, it becomes liquid. If you put heat to liquid, it becomes gas. If you put heat to gas, it becomes plasma. So, for example, molecules or atoms may be stripped of their electrons by external radiation coming from the sun, or the second way of ionizing our upper atmospheric region is by precipitation from outer space. So actually the ionosphere is not the outermost part of our space. So if we think about our planet as a system, we have the planet, which is the body, where we live now.
Yep.
We have the atmosphere on top of it. Then we have the ionosphere on top of the atmosphere. And above that, we have what is called magnetosphere.
Yeah.
And magnetosphere is our magnetized domain, which is controlled by our planetary magnetic field. And this magnetic field is very dynamic.
Right.
And it accelerates those particles which are coming from the sun in processes which are internal to our magnetosphere. And those processes then launch those particles and they precipitate into the atmosphere. And those energetic particles which are coming from our space, accelerated by our processes within our magnetosphere, they strip those electrons out of those atoms and molecules.
Right.
So in summary, we have two ionizing mechanisms. The UV radiation from the sun,
right,
that kicks electrons out of the atoms and molecules and therefore makes plasma. And then these acceleration processes in the magnetosphere, which precipitate particles into the atmosphere and kick those electrons out of those atoms and molecules. And in this process, we also see the great aurora, which we can see here in Finland. I don't know if you guys can see it in the continental Europe, but
not here in southern France. But I've lived in North America and certainly have seen aurora. Yeah, and it's wonderful. Here's a really good question that I think people don't understand. They kind of see a model of the Earth and a map, and they think the atmosphere stops. And I don't think it really stops. I think it just fades away, and there is a percentage of less and less and less. But would you agree that our planet has a kind of the atmosphere doesn't have an end; it just gets weaker.
Yep, exactly like this. So at some point, at Earth, here where we are now, we are in 100% atmosphere, and then still in about 60 kilometers of altitude, we are still in the 100% atmosphere. But then starts this transition region where there are lots of gradients in all parameters, in density, temperature, ionizing, the fraction of particles that are ionized, very many parameters that are rapidly changing. And actually, it is this layer now from about 80 kilometers to 120 kilometers and sometimes even 600 kilometers, where we are talking about, actually, I'm very often using the word Ionosphere,
right?
Because we don't know so much about this region. So in effect, we are first in the atmosphere. Then when we go upwards, at some point we go into a transition region, which is a layer and in this layer, all parameters change rapidly, or within this layer they change. So at some point, then we don't have any, for example, oxygen atoms anymore.
Right.
But
we still have our atmosphere as it gets ionized and as it moves out to a tremendous distance, to a point where your wonderfully coined Ionosphere goes way up into space, to the point where it could even interact with things in orbit.
Yes, exactly. So I would say that our planet consists of atmosphere, ionosphere, and the magnetosphere, because that whole system consists or makes our planetary near Earth environment. So things that happen far out in space, in the magnetosphere, they have a tremendous effect on things like aurora, which we can see by our eyes from looking at the surface of our planet. So basically, if we are limiting ourselves in talking like our planet is just this body, the sphere, it's not so, because there are several phenomena which are affecting our daily lives, which are born in space.
Out there, right.
That's right. And those are the most important regions for our daily lives here on Earth.
What it seems to me that what makes planet Earth so special is our magnetosphere, and the fact that we still have a stable atmosphere, unlike Mars, that apparently was his atmosphere was possibly eroded due to
that's
the lack of magnetism. The big takeaway is that our atmosphere transitions and slowly fades away to a tremendous height. Let's talk a bit more about the ionization process. When we talk about ionization, and you clearly talked about plasma being the fourth state of matter, are these molecules, are these atoms of the atmosphere that we breathe down on Earth, do they still exist? Tell us more about what is plasma and how does it work? I mean, is it still oxygen and carbon dioxide and nitrogen?
Yeah, this is an excellent question. So we have different plasma regions in the vicinity of our Earth. If we start from the surface of our planet, the ionization starts at about 80 kilometers altitude, where we start to have electrons and then the constituents of the atmosphere in ionized manner, but only about 0.1% of the particles at this height are ionized. But anyway, the ionization, I mean, plasma physics is a field which investigates this fourth state of matter, so the plasma. And we already know that even if 0.1% of the particles are ionized, already that has clear plasma characteristics. And then when we go upwards from the 80 kilometers, at some point we start to have only electrons and protons. So those heavier elements of our atmosphere are mainly staying closer to our planet, and further away from the planet we have protons and electrons. And then when we go outside of our magnetic domain, called the magnetosphere, this is when we then go to solar wind, and in the solar wind we mainly have protons and electrons, some alpha particles. But so you asked, like, what is how does plasma work? Okay, here comes the definition. Plasma is the fourth state of matter, and it is a collection of charged particles where collective electromagnetic effects are important. So we are basically talking about a gas where the gas is charged,
Right.
And it feels electromagnetic fields. It feels electric fields and magnetic fields. And then also other collective phenomena such as waves are important in behavior of plasma.
Okay.
So in our planetary system, our ionosphere and magnetosphere, we have, our planet has a relatively strong magnetic field, which is a dipole. And therefore we have this, for example, we can see that north is, we can see the northward direction from a compass because compass is reacting to the magnetic field. So our plasmas here near our planet, they feel our magnetic field.
Right.
And then there are all kinds of processes which create electric fields, and all those processes, magnetic fields, electric fields, and waves, control the behavior of the plasma. So we have lots of unknown and unpredictable processes here in Earth, which we do not know yet. But even so, they are affecting our daily lives because we have this thing called space weather. So similarly, as we have weather here on Earth, we also have weather on space, which is made up of these plasma characteristics. And those processes basically affect our satellite signals, the places where the satellites fly, I mean those orbits.
Right.
They can even affect our power grids on Earth. So there are several space weather phenomena which are born from these processes that we don't completely understand.
Oh, that's wonderful. Thank you. But we are very clever as humans. And tell me about when engineers and scientists first realized that a magnetic layer, an energized layer of the ionosphere could be used to bounce and transmit radio signals for a longer distance by reflecting off the Earth. Because we are surrounded by a field of energy which is magnetic. So you can affect it with RF energy and things. So tell me what you know about the history of the ionosphere and long-distance radio transmission.
Yes. So in the beginning of radio broadcasting, when radios were invented, those people who were launching those first radio signals, they noticed that those signals go much further than they were kind of calculating.
Right.
And they kind of deduced that there has to be a layer above our Earth in where the radio signal is reflected. And this layer was called then E for electricity.
Right.
And today when we are looking at those ionospheric characteristics, we still have the E layer. That's the most earthward layer of the ionosphere. And then after that, we have D and F layers. So the people who have studied the atmosphere took the E layer from these early radio transmission studies. And then the layers that were found afterwards were named D and F, like in alphabetical order from E. So so exactly from the early radio transmissions, we knew that we had to have an electrified layer above our heads.
And this is all these E, D, and F layers. They're all in what is called the ionosphere.
Yes.
They need to have the magnetic charge, the semi-plasma state to actually reflect radio waves.
So the radio waves are reflected already from the E layer.
Right.
And then those layers which are above the E layer, the D and F layer, they have different characteristics, and they are so distinctively different from the E layer that they have been given another name.
Oh yeah, that it's just so fascinating. So looking at the history of physics and looking at the history of military and weaponization, it seems that there was a great interest in the ionosphere because it could be a way, if only you could affect the ionosphere, you could possibly switch off long-distance radio transmissions. And weren't there experiments to look if you could modify the ionosphere in a way which would be beneficial to, say, switch it off for transmissions?
This is, again, a little bit out of my expertise area, but as far as I'm aware, there is still an active, one of the active research areas in ionosphere is called man-made effects. So there are, for example, there are heating experiments where people who are utilizing some heating facilities here on Earth, which are basically transmitters of electromagnetic waves. They send those waves above the atmosphere to the ionosphere, where they then these waves are interacting with the plasma and heating the plasma above in the ionosphere, and then they can kind of monitor, for example, by spacecraft or radars, how this heating was efficient. So this is one of the ways in which ionosphere is researched today, and this is called man-made effects. But I'm not very much an expert in man-made effects.
No, of course, and much of that research, although it takes place at universities, it's also very much seems to be military controlled, because there could be a weaponization or a military advantage by modifying the ionosphere. If the ionosphere can be modified by heating it, is it possible that the ionosphere could be used to deorbit satellites, low Earth orbit LEO satellites? Is that a program that you've ever heard about?
No, there are ways in which the atmosphere can be heated, or the ionosphere can be heated, which affects the orbits of the satellites. But I haven't heard that nobody has done that so effectively that it could, so that the man-made effects are not so effective as the natural effect. So the natural effect here is called Joule heating. So Joule heating is a phenomenon where an electric current goes through a medium. And this is exactly what happens in our ionosphere. So our ionosphere is a medium. It contains matter, and then there are these electric currents which are made by our magnetosphere, and they close through the ionized upper atmosphere, so the ionosphere. So effectively, it's like a water heater. So you put water into a heater, and then you put electricity on, and then the water heats. So when you have these electric currents that go through the medium, and when these currents intensify, that heats the medium, and it expands, like exactly as the same way we Finns go to sauna, and we throw water into the what is it called, the
little fire, and it makes steam.
It's called kiuas in Finnish, but we throw water into that thing, and then it makes steam, and that lifts upward. So you notice, for example, in sauna, you notice that the heated material is close to the roof, whereas your feet may be even cold. But anyway, so the same thing happens in the ionosphere. So when we heat the phenomenon heats the ionosphere lifts up. And then if you have a satellite here, you are a little satellite kind of going in the atmosphere, and suddenly something heats. You notice that, oh no, now I'm in a much denser plasma. So that heating increases friction on those satellite orbits. And what happens to the satellites? Satellite goes here innocently, then something heats up, satellite drops because there is additional friction in the satellite orbit due to this heating. And by the way, this exact process was behind the loss of the Starlink satellites in 2022, February. So there was a relatively minor space weather event which caused currents to go through the ionospheric medium.
Right.
And those currents heated the ionosphere, lifted the ionosphere upwards, and then the satellites were lost because their orbits were decaying. And this is an excellent example of those unpredictable things that we don't still know in ionosphere, because, for example, if we knew that there was going to be this Joule heating event when the Starlink satellite were launched, we could have told that, well, don't launch them yet because it's now a bad time to launch. But nobody was able to predict it because we understand it in qualitative manner. We know that this thing happens and it occurs, but we don't know how much the atmosphere lifts, and we don't know in kind of quantitative detail how this phenomenon works. And therefore we need science to still understand this.
So Finland, what's the connection, and why is Finland a center of excellence for the study of the ionosphere? Does Finland have a specific history and obviously geographical area in the world that makes it unique for studying the ionosphere?
Yes, so I'm the director of the Finnish Center of Excellence in Research of Sustainable Space, and one of the parts that we are researching in this Center of Excellence is the ionosphere. We are also studying the magnetosphere and the solar wind and the sun in the Center of Excellence, but ionosphere is part of it.
Right.
And why is Finland doing research in space? Well, it has to do with basically, I think, with two facts. One of them is that we have a long history of data records. So the first magnetometers that actually, I mean, if you put a magnetometer, it will measure space weather, because those space weather processes are creating magnetic disturbances, which you can then measure with the magnetometer.
Yes.
First magnetometer was established in Finland in 1838. 1838.
Right.
And this was also the start of the Finnish Meteorological Institute.
Right.
Finland established those magnetometers, and after that we have been measuring magnetic variations. And because we have had those data records and we have seen those aurora above our heads, we have started to think that what is going on, and therefore we have a strong space research community here.
Yeah, well done, Finland. And it goes back to the end of the 19th century. That's really interesting. Well, I think that we've covered a lot of really fascinating topics. I'd like to end by asking you specifically what your research is and what future exciting things are happening in your university with the ionosphere.
Yeah, so there are so many things that I could mention here, but first of all, we are developing the world's most accurate space environment simulation called Glaciator, and this gives an unprecedented description of the near-Earth space, so we can really start to see what's happening in space and start to understand these unpredictable phenomena, such as Joule heating, and which I mentioned.
Yeah.
Then we are. I'm also the author of a very exciting citizen science study, where the citizen scientists in Finland found a new auroral form, and it turned out that this auroral form was due to waves in this Ionosphere. So we were able to understand the ionospheric medium by looking at those aurora. So aurora was kind of a method for us to understand what's happening in the ionosphere.
Did this new phenomenon, does it have a name?
Yes, the dunes.
Oh.
And the dunes. So if you go, for example, into University of Helsinki website and Google dune aurora, you can find this exciting project.
My viewers on YouTube are absolutely fascinated by your research on the ionosphere, and I think you've made it so clear, and it's so good coming from you, a professor of physics, rather than me telling them. So thank you very much.
Thank you so much. It was really a pleasure. Yes.
And we'll speak soon. Thank you. Bye-bye.
Yes. Bye-bye.
Ionospheric heaters. The most famous one is named HAARP, based in Alaska. Credited with the military application of changing the world's weather, heating our upper atmosphere to deorbit rogue satellites. It's claimed it blocks international radio signals, and it's even credited to be able to send bolts of electricity out of the sky and mind control. But is any of that really true? Today, I'm highly privileged to share with you an interview with a real ionospheric heating scientist who knows exactly how it works and what it really can do. Meet scientist Antti Kero. Antti works in Finland's most important geophysical science university looking at our ionosphere, and he has access and uses daily ionospheric heaters left over from the Cold War. So let's explore the myths of ionospheric heating, the history, and the hidden truth. So, Antti, it's so great to see you, and thanks for joining us. Professor Palmroth covered the ionosphere so brilliantly for my YouTube viewers and the people who like my channel who are interested in science. But of course, they all asked me about ionospheric heating and all the conspiracy theories about ionospheric heating. And I thought today it would be great to speak to you, somebody involved in that science and that field, and to dispel some myths and to go over what actually is going on with human intervention with the ionosphere. So my first question is, doing some research and what I basically know from my science research is it true that it became possible that the ionosphere could be modified due to Radio Luxembourg modifying modifying other people's radio transmissions when they bounce, as we know, off the ionosphere? Tell us about the Luxembourg effect, and when was that?
Yeah, thank you very much for the invitation, first of all, and it's very nice to talk about heating as a scientific perspective. And you are absolutely right. This so-called Luxembourg effect was the first heating experiment, although it was unintentional one. It was in 1930s, 1933, and at that time, well, obviously radio was invented, and also it was invented in this famous Marconi's experiment that radio waves can be propagated, or ionosphere can be used as a mirror for radio waves.
Right.
And in this, what happened in this Radio Luxembourg case was that there was another amplitude modulated radio station. I think it was the transmitter was in Peromünster, and the receiver was in Eindhoven.
Right.
And this very powerful Luxembourg station was in the middle.
Yeah.
And it turned out that you could here in the background of this other radio station from Beromünster, also this Radio Luxembourg, and that was a puzzle because that was totally in a different frequency, and it was explained in a scientific journal Nature later that in fact the possible mechanism which caused this cross modulation was actually heating of the radio path between the transmitter and the receiver.
Right.
So this Luxembourg station as amplitude modulated station that was capable of modulating
Right.
the ionosphere, which act as a mirror in between the transmitter and the receiver. So that was really the early invention of man-made experiment in space in this sense.
It's just a brilliant story. I remember back in the 60s, somebody told me that Radio Luxembourg was so powerful that somebody managed to take an induction coil in their chicken house and use it to heat the chicken house, which I think is just fantastic. Anyway, that's just brilliant. But so I take it that the Luxembourg effect was observed, and some smart person, and I would have thought that, maybe it's possible that we could attenuate or modify somebody else's radio broadcast by affecting the bounce layer, one of the ionospheric bounce layers. And so I'm going to use the word carefully. It was the first idea that this outside part of our atmosphere could be weaponized. So was the first applications for human intervention into the ionosphere a military project before science came along?
Well, I don't think that the military application was so much to do with disturbing the radio transmissions. The reason why I'm skeptic about this is that this frequency modulation, which was invented later,
right,
that actually solved the whole problem. I mean,
right,
frequency modulation is much more robust against the amplitude changes, and that basically solves the problem. You are right in the sense that in the very beginning of these heating experiments, military applications or military organizations were very interested in this. But the reason was more to do with using the ionosphere as a huge radio antenna. Because by modulating the currents, or basically conductivities in ionosphere, makes it possible to use or to use ionosphere as a very long wavelength transmitter for radio waves, VLF waves.
right.
And that in turn is very useful for communicating to submarines.
So the ionosphere, the idea was the whole of the Earth, or a large section of the ionosphere, could be vibrated by radio frequency for VLF waves. And so a submarine at a long distance could pick up a message. Is that?
Yes, something like that. Of course, it is relative what is the large part of the ionosphere, but basically the ionosphere above the heating facility can be modulated. So it is typically something like 10 degrees wide beam, and obviously in the in the global scale, that is a very tiny spot in the sky which is modulated, but nevertheless that can be used as a larger antenna. And but the problem in that system is that worked very nicely in some days, but then when the ionospheric conditions are, let's say, disturbed in the wrong way or too quiet or something, then this mechanism is not that suitable for sending these waves. Or
Right.
and these transmitters for the submarines, which are basically nuclear submarines under the water, it's strange to think, but they don't know if the nuclear war has started
Right.
over there. So there must be some kind of beacons explaining them that we are still here.
Right.
Don't push the button.
Right.
So we cannot use anything unreliable for this kind of messages.
Right.
And I think this military interest on this heating experiment was more like a prototype rather than the actual method of communicating those soldiers in the submarines that we are still here. And that's why there are special transmitters designed for this purpose only, and they are not hitting facilities.
They're combined VLF or ultra ULF stations that also could use the ionosphere to communicate with submarines. They're often associated to send out this "don't fire your missiles, hold" message, which is the constant message, which all you need to do is to tune in to check that it's still saying the world is safe, the world is safe, don't fire.
Well, obviously I mean, it's classified what they send.
Right.
Those are also modulated transmissions, basically coding some kind of message. And of course, we don't know what is that for sure, but perhaps they are some kind of beacons for navigation, and perhaps the message is very simple.
Right.
That everything is fine, and so that is my. Obviously, I'm not a military scientist, so I don't know much about it, but this is my educated guess what is going on.
Next question. So so that turns the whole thing on its head. I always assumed that the military were interested in turning off radio transmissions, and you've just totally said the opposite, which is so interesting, that they were using Ionosphere as a giant transmitter. Why do you think the early most of the man-made ionospheric heaters are in extreme polar latitudes? Well,
that is to do with the academic interest in heating science, and that is basically where the auroral oval and radiation belts take place.
Right.
If you think about the magnetic field of the Earth that hits us in the magnetic poles, of course, and that is where you have energetic particle precipitation from the Earth's magnetic field or Earth's magnetosphere. And so most of this interaction between the space weather and atmospheric interaction that happens in the polar latitudes, and heating science is aimed to study these effects kind of in an active way. One other thing is that these heating experiments are they benefit from the vicinity of other instruments which are supporting these measurements and basically are used for measuring these heating effects.
Right.
So the one which I have been using, which is this IceCat heating facility, that is obviously next to the IceCat radar.
Right.
And it is there because IceCat radar is there, and IceCat radar is there because it's an interesting place.
Right.
So like in terms of magnetosphere. So I think that is the reason. But one of the first heating facilities one of the heating facilities made in the 80s was in Arecibo, so it wasn't so high in latitude.
Yeah, no, the Arecibo story is just absolutely fascinating because it kind of breaks away from the polar positions of Alaska and Norway, Finland, and maybe Antarctica. But let's bust some myths about Arecibo, because everybody thinks Arecibo is this SETI radio telescope that we've all seen in the film Contact. And sadly, it fell down. Probably due to lack of maintenance and lack of funding. But if you really look at the history of Arecibo, and you've already mentioned it in the context of an ionospheric heating station, isn't it true that there's an ionospheric heater, or there was an ionospheric heating radio antenna, and that the Arecibo dish was actually is a radar dish looking for the effects of this heating? Was that its main role when it was first built?
Yes, it was a radar in the first place,
right?
But no for the heating experiments. That was later addition. But well, the story of Arecibo radar or facility started because it was there was a theory that you can have incoherent scattering from plasma from ionosphere, but they calculated that will be so tiny backscattering that you need to have this kind of huge antenna in order to see that backscattering.
Right.
So the collective area or collection area for this tiny bit of backscattering from, let's say, megawatt range transmitter, so tiny bit comes down from these free electrons from ionosphere. That was basically calculated, and then it turned out that this backscattering is still very tiny, but it is much stronger than expected.
Right.
So in fact, that was a bit of an overkill to make this kind of huge antenna.
Yeah. Right.
And that was it's a bit technical, but the early scientists or early theoreticians, they didn't understand that scattering is actually enhanced by the fact that electrons are not that free in plasma, but they have to move along the ion acoustic waves, and that is very beneficial for this business. So I think this antenna was roughly by factor of 10 to big to. I mean, they just wanted to see something, and the backscattering was much stronger. But on the other hand, that turned out to be very beneficial for many science applications, not only the radar, incoherent scatter radar business, but also the radio astronomy and SETI. So Arecibo radar was the largest and most beautiful radar in the world, and it's very sad that in 2020 it was destroyed by
the hurricane. Yeah.
Hurricane, and that was the end of it, really.
Yeah, it's unlikely
Or-
that it'll be rebuilt.
Yeah, I hope that U.S. Funding agencies come to their senses and rebuild that.
Oh, that would be, it would be great. But it's good to bust some myths, because I don't think people really understood why it was built and what it really did and what its capabilities, its major capabilities were. Although, as you said, it did have other functions as they put in different antenna later in its life. Oh, so that's fantastic. So atmospheric heating is not going to send a beam of death into your house, and it's not going to change the world's weather. And it's also probably going to be very hard to make an ionospheric heater that would deorbit a satellite. And that's a lot of people are interested in that. Was there research in, the kind of oversimple idea is if the part of the ionosphere could expand into the path of a low Earth orbit satellite, you could maybe slow it down to a point every time it went round, you could target how it was deorbited. Is that a complete myth? Obviously, it does work, because as we talked in the last film, when the ionosphere naturally expands due to space weather, it can affect low Earth orbit satellites. But have you ever come across any projects that could literally deorbit a satellite from Earth?
Well, to me, it sounds a bit science fictional. First of all, I think many of these misunderstanding concepts related to heating experiments are because the heaters don't really heat the atmosphere.
Right.
They heat the electron gas or plasma in the ionosphere, and ionosphere is partly ionized part of upper atmosphere. So we call that ionosphere, where solar precipitation or solar X-rays are,
right,
or EUV is detaching electrons from neutral atoms that makes a pair of positive ion and electron, and that is called ionization. Okay, perhaps these things you have already covered.
No. It's good to repeat what plasma is and what ionization is, and you've just done it very clearly. Thank you. Yeah.
So I just want to point out that this electron heating is really electron heating. So even the ions are not heated in the in these experiments, because ions are very heavy compared to electrons.
Right.
Electrons are very sensitive on very tiny radio wave intensities.
Right.
So if you calculate the intensity of the most powerful heaters in let's say 100 kilometers,
right,
then the intensity is some milliwatts per square meter. So it is clear that it is not any Death Star capable of pretty much anything. It is a very tiny energy, which is still important for the electrons, because they are easy to they are small and they are easy to move back and forth, and as a consequence, this electron temperature can be increased by these heating experiments by factor of 10 quite easily.
Right.
So, and many phenomena in the ionosphere, let's say conductivities or chemistry, or also plasma phenomena, they are electron temperature dependent. So we can use the ionosphere as a space laboratory or space plasma laboratory and do active experiments
Right.
So there is lots of potential of making these kind of effects which are dependent on the electron temperature genuinely, but there are also very serious limitations in trying to let's say change the trajectories of satellites.
Right.
So one could imagine that we enhance, let's say, ion outflow because of there is some evidence that can be done, and perhaps that could have some kind of impact on satellites. But I would say that no, it doesn't work, because it is simply these energies needed. It is hard for me to see that
Right.
not to mention that we are changing, let's say, weather,
Right.
because the energies needed to change the weather are completely in different order of magnitude. So these heating facilities, they use typically megawatt of power or 2 megawatts of power. That sounds big, and the electric bill is quite big, but still, if you think about 1 megawatt of power in Finland, we use electric saunas.
Right.
So a small village turn the electric saunas on every Saturday at the same time, and that equals to this heating.
It's the
power.
same, right?
So yes, and someone calculated that if there is an asphalt below the antennas which are
Right.
used for these heating facilities, the solar power absorbed by this asphalt is greater than the electric power.
That's
So
great.
so that may puts that into perspective that
It does.
that
It does. Yeah. So we're coming to the end of our time that we have. So let's quickly talk about what your current research is and an exciting new developments in Finland.
Yes, we have recently launched, or recent years launched, our first satellites. These kind of microcube satellites, which are very popular at the moment, these few kilograms payload satellites, and the recent paper I was involved with my colleague Esa Kallio, using the so-called Suomi 100 satellite, which translates to Finland 100.
Okay.
That was Finland 100 years celebration satellite.
Okay.
And that had the radio receiver on board, so we could listen to the actual trans-ionospheric propagation of the heating signal. And we could, for the first time, measure this kind of nonlinear effect, that when we send this radio wave up to the skies, it really heats the ionosphere,
Right.
and that changes the propagation of that very same radio transmission. So we were kind of doing the Luxembourg effect to our own signal,
Right.
and that has been known that should take place, I mean, since really the Luxembourg effect, but this was the first time it was measured from the space, I mean, through the ionosphere.
No, that's fascinating. Yeah.
Yeah, so that was quite nice kind of demonstration of well, the power of these small satellites. They are capable of doing real science in some reasonable money.
Right.
And also this that was basically basic research related to this
Oh, that's fantastic. I will.
Old radio science, but also it really emphasized how tiny is this effect, or how modest is actually this intensity of the radio wave, because it was, for the dedicated radio receiver, it was you could hear this signal only something like a few seconds,
right?
Because that is when the satellite was in the beam of the heater, and yes, so to change the trajectory of that satellite, and to actually hear the signal, it is totally different ballpark of a problem, and
right.
Yes, so that is what I have been recently doing with heating experiments. Obviously, I'm interested more broadly on interaction between the solar activity and space weather and the polar region ionosphere. So that is my framework, but and heating experiments, that is just one aspect of it, but.
Oh, it's great, and I'd love to talk to you longer about this. You've covered so many good topics, but we're coming to the end of this Zoom call session, and I'd just like to thank you so much. I will put links to the CubeSat and your research for my viewers to read you about your work. But and Antti, it's just brilliant. You've busted so many myths. And you've put our world into context about the size of our ionosphere and how minimal we are as humans in actually affecting this global part of our atmosphere. So thank you very much for today. And it's been an absolute pleasure to talk to you and all your wonderful work in Finland. Thank you.